welcome to day 2. Today we're going to talk about how we define an acid, how we actually identify and figure out what's acting as an acid in our solution, and also how we figure out how strong it's going to be. So you may remember from yesterday, we talked about your initial definition of acids and bases, and it was probably that an acid is anything that increases the concentration of hydrogen ions in your solution, whereas a base was anything that increased the concentration of hydroxide ions. Now that starting point is called the Arrhenius definition of an acid and a base. And that is a very useful starting point. Arrhenius said that an acid was any substance that, when dissolved in water, would increase the concentration of hydrogen ions, and a base was anything that, when dissolved in water, would increase the concentration of hydroxide ions. So in the case of hydrochloric acid, for example, we know this is an acid because when it's dissolved in water, it splits apart into hydrogen ions and chlorine ions, and so the end result is an increase in hydrogen ions, so we meet the definition for an acid. Similarly, sodium hydroxide dissolves in water to produce sodium ions and hydroxide ions, and so does increase the concentration of hydroxide to meet the definition of a base. Now, if you're thinking about this definition, you might notice one pretty obvious limitation, and that is that both of these definitions depend on the substance being dissolved in water. Both the acid and the base definitions include the provision that when this substance is being dissolved in water to have this effect. So this just completely excludes any non-aqueous acid or base. Any solution that doesn't have water as its solvent would not fit into this definition. So for our purposes, we need a more adaptable definition, one that doesn't have that limitation of requiring water. And so we are going to move on to what's called the Bronsted-Lowry definition. Now this is very similar, but like I said, it can be applied to any substance, not just an aqueous one. So according to this definition, an acid is just any substance that's a proton donor, any substance that gives up a proton or gives up a hydrogen ion to the solution or to another substance. Meanwhile, a base is the proton acceptor, a substance that accepts that proton, that hydrogen ion. So we can use this definition and apply it to the hydrochloric acid just like the last definition. So hydrochloric acid, when dissolved in water, loses its hydrogen to the water molecule because the hydrogen ion that was attached to the chlorine leaves the chlorine to go form the hydronium ion. The HCl, you can see it here drawn out with its Lewis structures. The HCl donates the hydrogen, its proton, and that proton, that hydrogen, goes and bonds with one of the non-bonding pairs of electrons on oxygen to make the hydronium ion. So in this case, the HCl is clearly the acid because it is what is giving up a hydrogen. We can tell it's the acid in this case because when we move from the reactant side to the product, this is the compound that has lost a hydrogen. It donated it. Meanwhile, for this reaction, the water is acting as a base because it's accepting that extra hydrogen. When we go from the reactant side to the product, it is this molecule that has one more hydrogen, and so it acts as the base here. So to be a Bronsted-Lowry acid, the substance must have a removable proton. That's pretty much always in the form of a hydrogen ion. It has to have a hydrogen as part of its Lewis structure as part of its molecule that it can give up and lose and donate. A base in this definition must have a pair of non-bonding electrons that it can use to attract that proton. Here's one more example using this definition. I want to show you the case of ammonia again, because as we saw in the last lesson, ammonia is a special type of base. And now it's easier to see why ammonia gets the definition of base. If we look at ammonia before the reaction on the reactant side, and then look at it after, we can see that it has gained one hydrogen. It has gained a proton, it's gained a hydrogen ion, and so it has acted as the proton acceptor here. It meets the definition for a base because it gains a proton. Meanwhile, it's the water in this case that's acting as our acid, because if we look at it from the reactant side to the product, we can see that it is losing a hydrogen. It has one less hydrogen now, one less proton, and so it meets the definition of the acid. It donated its proton, its hydrogen, to the ammonia. Now you might have noticed something here if you were paying attention to the water. Let me go up a slide. When we had hydrogen chloride making hydrochloric acid, it was the acid and the water acted as the base. The water accepted a proton. Here with ammonia, the water acts as the acid. The water donates the proton. And so there are a couple substances like this that can be either the acid or the base in the reaction. And these types of compounds are called amphiprotic. They can be either. Water is a really common one. There are a couple of others. And these are just sort of, they're in the middle. They are in the middle between really strong acids and really strong bases. And so they can act as either as necessary. If you put water with a really strong acid, it will act like a base. If you put water with a really strong base, it will act like an acid. So let's take a closer look at what is actually happening in these reactions when an acid or a base dissolves in water. So in the case of, again, hydrochloric acid, we've got hydrochloric acid here. We know it's the acid because it is what is losing a hydrogen and it's giving it up to the water. So water is acting as our base. It's going to accept that hydrogen ion to form the hydronium ion. And what is formed as a leftover from the hydrogen chloride is called the conjugate base of the acid, of the hydrogen chloride. A conjugate base is just what's ever left over after the acid donates its proton. The leftover, in this case the chlorine ion, is its conjugate base. Here's some more information on that. Every reaction between an acid and a base will have a conjugate base and a conjugate acid. So if you react an acid and a base, the products will be the conjugate base and the conjugate acid. Every acid and every base has its conjugate pair. So in this example, first we'd look at this equation, we'd figure out which one of these substances was our acid. So we'd look at the reactants, we'd look at the products, we'd ask ourselves which of these things lost a hydrogen. Which of these two reactants lost a hydrogen in the reaction? And we can see that NO2 here is missing its hydrogen. This is our acid because when we go from reactant to product, it loses its hydrogen. So we know that this is the acid. Meanwhile, we know this is the base because it is gaining a hydrogen. And so this reactant product pair is a conjugate pair. The acid has a conjugate base that is the same substance just with one less hydrogen. It's what's formed when the acid donates its hydrogen. The base has a conjugate acid. It is what's formed when the base accepts an extra proton. And so these will always come in pairs. Here's some general information about these pairs. Whatever is left of the acid after its proton is donated is that acid's conjugate base. And whatever remains of the base after it accepts a proton is that base's conjugate acid. So for the general reaction shown here, this is HA. Any acid, a hydrogen bonded to anything else. If this is an acid, then it's going to donate this hydrogen to the water molecule to form the hydronium ion, and the leftover is its conjugate base. So these conjugate acid-base pairs will always differ by just one proton. This conjugate base has one less hydrogen than its acid did. Meanwhile, this conjugate acid has one more hydrogen than its base did. Here's one more picture to demonstrate that. Again, looking at ammonia acting as a base. Now here we can tell ammonia is the base because if we look at it going from the reactant to the product side, it's clear that it is gaining a proton. It's accepting an extra hydrogen, so it's the base here. Meanwhile, the water is losing a hydrogen, so it is the acid here, and each has its conjugate pair. You can see maybe more clearly in the drawing up here that these conjugate pairs are just one hydrogen apart. That's the only difference between them. Alright, here's two examples for you to try. We want to do two things. We want to first identify which reactant is our acid and which is our base. And secondly, figure out, identify each acid-base pair, each conjugate pair. So you can take a couple minutes, pause if you need, and think about that. And then we'll talk about the answers. Alright, so hopefully your work agrees with this. In the first example, we've got the HNO3 as our acid, and we know that because when we look over to the product side, we see that the NO3 is missing a hydrogen. So this was our proton donor. And the NH3 was our base, it was our proton acceptor. It gets one extra hydrogen on the product side. And these are color coordinated to identify the conjugate pairs. So this is our acid and our conjugate base. This is our base and our conjugate acid. Similarly, in this example, we know this is our acid. It is missing one hydrogen over here. This is our base. It has one extra hydrogen over here. And again, the blue is our base and our conjugate acid. The red is our acid and our conjugate base. Now we could line these up in this table. We have an acid across from its conjugate base. A couple of examples down here. An acid, its conjugate base. And as we go down, we get weaker and weaker acids, stronger and stronger bases. We could start talking about bases and their conjugate acids. So this is actually a really important relationship. Strong acids are going to completely dissociate in water, meaning their conjugate bases are extremely weak. Weak acids here in the mid-range are only going to partially dissociate in water. Their conjugate bases are weak bases. The weaker the acid, though, as we go down, the stronger its conjugate base gets. Similarly, substances with negligible acidity, very weak, almost no acidity, are very strong bases. These do not dissociate in water. The conjugate bases are extremely strong. Water, for example, has almost no acidity. It's very low on this scale, but its conjugate base is the hydroxide ion. It's what our first definition of a base was based off of. It's a very strong base. So in general, the stronger the acid is, the weaker its conjugate base. The hydrogen ion is the strongest acid that can exist in equilibrium in an aqueous solution. Meanwhile, the hydroxide ion is the strongest base that can exist in an aqueous solution. So if we're talking about the strength of acids and bases in any reaction, the equilibrium is going to favor the reaction that moves the proton to the stronger base. So the reason we care about figuring out the relative strengths of these is so that we can apply our knowledge of equilibrium from the past unit to figure out which side of this reaction is going to be favored. So for this example on this slide, water is a much stronger base than the chlorine ion. I'll go back to the table in a second so we can compare those. This is going to tell us that the equilibrium lies very, very far to the right. This is heavily product favored. K, our equilibrium constant, is much, much, much greater than 1. This reaction will essentially go to completion. Let me go back to this table really quick to show you the comparison between water and the chlorine ion. So here we've got water is a weak acid, and the chlorine ion is the weakest base listed. So as far as these two are concerned, oh, here's water on the base scale. Water is a stronger base than chlorine, and so this reaction that involves the two of them is going to favor the side that has the extra hydrogen ion on the water molecule. So this side is favored because this base was stronger. It got to accept the proton. That was much more favored than having the proton on the chlorine, which was a much weaker base. Let's look at another example. If we were to compare acetate and water, we would find that acetate is a stronger base than water. So the equilibrium favors the reactant side, the left side in this case. We would know that the equilibrium constant K must be some value less than 1 because we need the hydrogen ion to be attached to the acetate. This is a stronger base of this pair. So we would rather have the hydrogen here than here. We have it on the stronger base of its two options. Water, again, remember, is one of these substances that could be either an acid or a base, depending on its situation, on its circumstances. So if we had just pure water, we would actually find that at a given moment, some of it is existing as a hydronium ion, some as a hydroxide ion. This is called the autoionization of water. This idea that you've got some water acting as a base, some acting as an acid in the solution. The hydrogen ion's not really sure where to go because it could go either way. And so if we needed to write an equilibrium constant for this, we would call it the ion product constant. We'd write our equilibrium expression just like the last unit, where our equilibrium constant K is equal to the concentration of our products. So our possible products here were the hydronium ion and the hydroxide ion. Notice these are the only two concentrations that appear in our expression, because they are the aqueous ones. The pure liquid phases do not appear in the equilibrium expression because they don't have concentrations. Now this is a very special equilibrium constant because we're talking about water, and water tends to be special. It is called the ion product constant for water, or to make that shorter, Kw. The Kw for water is 1 times 10 to the negative 14th. And we'll use that number in several ways. Again, if this rings a bell from yesterday, we used the K factor of water, 10 to the negative 14th, to convert between hydrogen ions and hydroxide ions. And now we can see why that worked. So in most solutions, the actual concentration of hydrogen ions is fairly small. That's why we use the log scale. And we saw this yesterday. Our pH equation is the negative log of the hydronium ion or of the hydrogen ion. Like we said, these are interchangeable. Whereas the pOH scale would be the negative log of the hydroxide ion concentration. And we know that water has a pH of 7. It also has a pOH of 7. Acidic solutions will have a hydrogen ion concentration that is greater than 1 times 10 to the negative 7th, greater than the concentration of water, and so a pH that is less than 7 because of that relationship. If this concentration is greater, it's going to be 1 times 10 to the negative 6 or the negative 5th, while a pH of 5 or 6 less than 7. Similarly, for a basic solution, if the concentration is less than 1 times 10 to the negative 7th, maybe it's 1 times 10 to the negative 8th or 9th, the pH will be greater than 7. It will be 8 or 9. So the higher the pH is, the lower the pOH is, and the more basic the solution. Here is a table for your reference of the pH values of some common substances. You can use that later to come back to. Now, I briefly mentioned this in the lesson before. The P in front of all these scales is just indicating to us that we're taking the negative log of whatever quantity we're talking about. So the pOH scale is the negative log of the hydroxide ions. We could apply this P to the ion product constant of water and get the negative log of this Kw. And check this out. Let's do it, just because. So if we applied this, we know that Kw, we wrote this expression out earlier, is equal to the concentration of the hydronium ion times the concentration of the hydroxide ion, and we also said that it was always equal to 1 times 10 to the negative 14th for water. So let's apply the negative log to everything in this line. So the negative log of this product could be split apart because of log rules into an addition problem. So we'd have the negative log of the hydronium ion concentration plus the negative log of the hydroxide ion concentration. If we apply a negative log to Kw here, and the negative log of 1 times 10 to the negative 14th will be 14. So in other words, what we're saying is this is the pH. This was the definition of pH, the negative log of the hydronium or hydrogen ion concentration plus the negative log of the hydroxide concentration, that would be pOH, is equal to the negative log of Kw would be pKw, is equal to 14. In other words, the pH plus the pOH is always equal to 14. If you know the pH is 4, the pOH must be 10, and vice versa. And this is why we are able to use the K factor of water, 10 to the negative 14th, to figure out what our hydrogen ion or hydroxide ion concentration is given the hydronium ion concentration given the hydroxide ion concentration. If we know this, and we know this, we can simply solve for this as we did yesterday by taking 10 to the negative 14th divided by this number. All right, that concludes the information for today. Let me know if you have any questions. Thanks again for watching.